Okay, so in the last video, we started learning about the power rule. I just want to add a couple notes about that. So there are certain functions that look like they don't use the power rule, but they do if you just use their properties. So for example, something like 1 over x squared can actually be rewritten as x to the negative 2. Remember, when you have a negative exponent, you put the x on the denominator and make the exponent positive. So actually, the derivative of this becomes negative 2x, and you still subtract 1 from the exponent, so it becomes negative 2x to the negative 3. So another example would be 2 over x cubed can be rewritten as 2 times x to the negative 3. So then f prime of x becomes negative 6x to the negative 4, which is actually negative 6 over x to the 4. Okay. Another one is when you have something to the 0th power. So for example, 5x to the 0. Keep in mind that anything to the 0th power is just equal to 1. So this is actually just 5, and the derivative is then 0. Okay. So another example. So if we have something like 5 plus 3x to the 0 minus 2x squared, f prime of x, well, this is a constant, so there's 0. This is 3 times 1, which is just a constant, so the derivative is 0, and then this becomes minus 4x. So our derivative would be minus 4x. Okay? So that's just a couple more applications to the power rule. Another one, last one, would be if you got something like the cube root of x. This is actually rewritten as x to the 1/3. Okay, whenever you have a root of something, you can just write it to the 1 over whatever root you have. So then the derivative would be this multiplied to the coefficient, and then you subtract 1. So 1/3 minus 1 is 1/3 minus 3 over 3, which is equal to negative 2 over 3. Okay. To simplify this, it would become 1/3 x. So you see how it's to the negative 2? That means it goes on the bottom. Okay, let's erase this. It actually goes on the bottom here. Squared. And this over 3 means it's a cube root. So the cube root of x squared. Okay. Let's do another quick example of that. So if we do something like this 3 times the square root of x can be rewritten as 3 times x to the 1/2, which is then the derivative becomes 1/2 times 3x to the 1/2 minus 1, which is equal to 3/2 x to the negative 1/2, which is actually 3 over 2 times the square root of x. It's on the bottom because you have a negative 1. Puts it here, and then the over 2 means it's a square root. Okay, so that's for the power rule. Okay, let's move on now to secants and tangent lines. Okay, we have learned so far about average rate of change, or AROC for short. Okay, we can find the average rate of change by finding the slope of the secant line. Okay, so for example, let's do the function x squared. Okay, so it just looks like this. Here's my x squared. At 0, we're at 0. At 1 and negative 1, we're at 1. At 2 and negative 2, we're at 4. Okay, and let's say we want to find the average rate of change at x equals 2. So right here, we can draw a secant line. And let's do it at x equals 1, actually. Okay, let's say we want to find the slope of the secant line at x. So let's draw well, one option might be to draw a secant line between x equals 2 and x equals 1. So there's our secant line. And then to find the slope of that, so my secant line, the slope would be the change in y over the change in x. Okay? So my change in y, well, my point here is at 1, 1. My point here is at 2, 4. So then my change in y is 4 minus 1 over 2 minus 1, which is 3 over 1, which is 3. So that's my average rate of change. Well, to get a more accurate rate of change, I can draw a secant line that's even closer to the value I want. So maybe instead of at 2, I draw it at 1.5 over here. There's another secant line right there. Now at 1.5, my value is 1.5, and then my function is x squared, so I got to square 1.5, which is 1.5 squared, which plug it into our calculator real quick. 1.5 squared is equal to 2.25. Okay, so then those are my 2 points, 1, 1, and 1.5, 2.25. So then let's find my average rate of change there. Again, it's my change in y over my change in x. So don't get confused just because I changed the notation here. This is still my y value at these x's. So my y value is f of 2.25 because I plug in, sorry, f of 1.5. Because my input is now 1.5 minus f of 1, which that's my x value, the other x value I want. Okay, so at this, my f of 1.5 is 2.25. F of 1 is 1. 1.5 minus 1. And so my slope here would be 1.25 divided by 0.5, which is equal to 2.5. Okay, so that's a different slope than the one I got here. You might again try to get a more accurate slope by going even closer. So instead of 1.5, maybe we can draw the slope at 1.25. So right here, that's even closer. There's my secant line. My average rate of change would then be f of 1.25 minus f of 1 all over 1.25 minus 1. So change in y over change in x. Okay, f of 1.25. So at this point right here, my point is 1.25 squared. Again, because that's my function. So 1.25 squared happens to be 1.5625. So then we have 1.5625 minus 1.25 over 1.25 minus 1, which is equal to 1.25. So as you can see, as our x value gets closer and closer to the x value I want right here at 1, okay, then the flatter and flatter our slope becomes. And you can see that happening. So at first it's really steep, then it gets flatter, and hopefully more and more accurate. So that's our goal, is to get so accurate, want AROC so accurate that it looks like our IROC, which is our instantaneous rate of change. So rather than an average rate of change, we want the actual rate of change at the instant x equals 1. So want IROC at x equals 1. So the way we do that is we pick points that are closer and closer to the actual point we want so that we are as accurate as possible. So in general, okay, if we have a function, let's say here's our f of x there, okay, and we want the slope at a certain point, x, okay, and the y value there is f of x, okay, we want to pick another x value some distance away. This is our secant line. So let's say we pick something h units away. So our new x value is x plus h. The y value there is f of x plus h. Okay, that's just another new x value that's h units away. Okay, then we can make a secant line and find the slope of that secant line. So this is our average rate of change is the slope of that secant line, which is our change in y over our change in x, which is equal to f of x plus h minus f of x over h, because these x's cancel out right here. Now, to get a more and more accurate rate of change, we just draw another x value that's closer. So here's another closer x value, and a closer one, and a closer one. And what we're really trying to do is bring our point so close to x. We want to let it approach x. We want x plus h to get really close to x. To do that, h has to approach 0. We want this distance right here to be so small that we're essentially on the point that we want. So the IROC, or the instantaneous rate of change, is equal to the limit as h approaches 0 of our slope. So of our change in y over our change in x, which is just equal to the limit as h approaches 0 of x plus h minus f of x all over. Okay? And that's an instantaneous rate of change. That's the rate of change at the point we want. And this right here is the definition of the derivative, okay? The limit definition of the derivative. Essentially, if we have some function f of x, the derivative f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Essentially, what we want is to create a secant line and then let our x values get closer and closer and closer to the point we want that it starts looking like a tangent line. So we want our secant line to start looking like our tangent line. And that is what a derivative is, the actual rate of change at a specific value. Now, why do we do this? Well, to find the slope of a tangent line is impossible. To get a slope, to find a slope, you need 2 points, but a tangent line only goes through 1 point. So that's why we have to use this definition to actually get this slope right here. Okay? So that's the definition of the derivative. In the next video, I'll start showing you how to actually use it to find the slope or to find the derivative of a function.